So the second part of your notes for 2.3, we're going to look at the derivatives for the other trig functions. We only looked at derivatives for sines and for sines and cosines so far. And if you recall, the derivative for the sine was the cosine. And we went through that whole limit definition of the derivative to come up with that. And the derivative for cosine was negative sine. So now that we know those two, and now that we know quotient rule, we can find the derivative of the other four trig functions. So the derivative for tangent, if I rewrite tangent as sine over cosine, now that I know the quotient rule, I can find the derivative. So the derivative is going to be the bottom function, which is cosine, times the derivative of the top, and the derivative of cosine is cosine, minus the top function, times the derivative of the bottom, and the derivative of cosine is negative sine, all over the bottom squared. And if you simplify, you'll have cosine squared plus sine squared. You might remember cosine squared plus sine squared, that was the Pythagorean identity, is equal to 1. And 1 over cosine squared is the secant squared. So the derivative of tangent is secant squared. So you don't have to go through that process again. If you forgot it, you could do that, but you can just jump right to that answer there. And then cotangent, we could do the same thing for that one. Derivative of cotangent, well, if I rewrite cotangent as cosine over sine, that's going to be the bottom function, times derivative of the top, and derivative of cosine is negative sine, minus the top function, times derivative of the bottom, derivative of sine is cosine, all over the bottom function squared. And if you simplify, you have negative sine squared x in the top, minus cosine squared x in the top. If I take that negative out, this might look more obvious to you. So sine squared plus cosine squared is 1, but I have that negative out in front. And negative 1 over sine squared is negative cosecant squared. Right, and they're going to, all four of these kind of follow a pattern here. The derivative for tangent gave you positive secant squared. Derivative of cotangent gives you negative cosecant squared. They're kind of the opposite functions there. Now the secant and the tangent ones, these ones are a little bit different. These are not maybe quite as obvious as tangent and cotangent were. So to find the derivative for secant, if I just try to, and don't write this down, but if you try to write it as 1 over cosine, when we go to find the derivative, you would have the bottom times derivative of the top, which gives you 0, minus the top, which is 1, times derivative of the bottom, which is negative sine x, all over the bottom squared. This ends up canceling out. You'll have positive sine x in the top, cosine squared x in the bottom. You can write this down. This one works out fine this way. Right? And if you keep simplifying, then you could rewrite this as sine x over cosine x and 1 over cosine x. So you have two of those cosines. You have cosine squared in the bottom if you separate it into the two terms there. And then I usually write this first. Derivative of secant, 1 over cosine is secant x. And then this one, sine over cosine is tangent x. So the derivative for secant is secant tangent. And then last we can do this cosecant one. Cosecant we can rewrite as 1 over the sine. And then the same thing, the bottom function times the derivative of the top, and derivative of constant is 0, minus the top function, derivative of the bottom, derivative of sine is cosine, all over the bottom squared. That first term cancels out and gives you 0 with negative cosine over sine squared. Pretty similar to what we saw up here. You can see that it kind of follows this pattern. And if I separate this and make this just cosine over one of those sines times 1 over sine, we'd have, I'm going to put this one first. 1 over sine is the cosecant. Cosine over sine is the cotangent. And then let's not forget this negative here. So it's negative cosecant cotangent. So those are your other 4 trig functions. You can see they weren't too hard to develop there. You just rewrite them in terms of sines and cosines, something that you know how to take the derivative of, and then you can just take the derivative using quotient rule. All right, so you have some, in this homework, you have some trig derivatives that you're going to go through and find now. This first one, you already know how to do this. Sine x over x, if you use your quotient rule, bottom function times derivative of the top, minus the top function times derivative of the bottom, all over the bottom squared. And I know I say this formula backwards from what's in the textbook. They would put the cosine x first and the x second, minus, and then it would be 1 times sine x. It's the same thing. The multiplication can be in either order. That first term has to be first, and the second term has to be second, though. And then this doesn't simplify. And they want us to find the derivative at this particular c value, which is really just the slope for the tangent line. So I'll have pi over 6 times cosine of pi over 6 minus sine of pi over 6 all over pi over 6 squared. So 30 degrees, pi over 6. There's a 30, 60, 90 triangle with those ratios. So I have pi over 6 times the cosine for that triangle, so 3 over 2. The sine for that same triangle is 1 over 2. And then denominator is pi squared over 36. And if I simplify that first fraction there, and I want to get rid of all these complex fractions here. So the least common denominator for all of those is 36. So if I multiply the top and bottom by 36, the first term would reduce to a 3, so I'd have 3 root 3 pi. 36 times 1/2 will give me, what, 18? And then the 36 would cancel on the bottom. I get pi squared in the bottom. So there's some pretty crappy numbers for that one, but you know how to do that. For the next one here, just need to do some product rule. So the derivative, first function times derivative of the second, which is cosine. Derivative of cosine is negative sine, plus the second function, which is cosine, times derivative of the first, derivative of sine is cosine. And again, I say this in sort of the opposite order that the book does. It's just the way that I learned it. Once you simplify, you end up with the same thing. So we could leave this way if you want to plug in pi over 4 for your x. We could do that. And if you recognize that this is actually a double angle identity, you could rewrite this. That equals cosine of twice the angle. If you remember that, that's fantastic. If not, it doesn't matter. You'll still get the same answer here. So the sine of pi over 4, it's 45 degrees. I'll draw my triangle over here. So the sine for that triangle is 1 over root 2. The cosine for that same triangle is also 1 over root 2. So I have negative 1/2 plus 1/2, which gives me 0. And let's see what else we have in here. We'll look at this one, derivative for the secant. We just did this type of problem here, so derivative for secant. Derivative of secant is secant tangent. Derivative for tangent is secant squared. So you want to have those memorized. You want to know those really well. If you need to make some flashcards, make flashcards. It's more important to be able to figure these out and not have to do that product rule or quotient rule with them. All right, and then we can plug these values in. Secant of 5 pi over 3 is tangent of 5 pi over 3. Secant of 5 pi over 3, and then that thing is squared. So 5 pi over 3, that's 300 degrees, which is in this fourth quadrant here. So if I fill in some sides for this, That's a 60-degree reference angle, so the opposite side would be the negative root 3 and 2 and positive 1 in that first quadrant there. So secant, that's the reciprocal for cosine. So 5 out in front here. So the cosine would be 1/2, so the secant is 2. Tangent for 5 pi over 3, that's opposite over adjacent, so that's negative root 3 over 1. And then secant squared, secant again was the reciprocal of cosine, so that would be 2 squared. So it looks like I have negative 10 root 3 plus 4 for this one. Right, and we have 2 things left to do. One thing we've already talked about a little bit when we talked about velocity and acceleration, which is these higher order derivatives. And it just means that you're taking the derivative more than once. And we've looked at this notation where you had the double prime in there. We also looked at it this way. If you had s of t, the derivative for that was the velocity. The derivative of that was acceleration. So that was s prime of t, and this was s double prime of t. So we've looked at those a little bit in terms of velocity acceleration. Depending on what notation you use for the first derivative, usually will set up how you would set that second derivative. Dy over dx, we looked at this a little bit a couple days ago there. The second derivative looks like d2y over dx squared. Next notation, this is if you had just a single term, not an equation there. Just means take the derivative. And then this last notation, I've never seen this last notation used. Doesn't mean it can't happen, but I've never seen that one used in problems. So really these first 3 are the most common that you will see. So higher order derivatives, you just keep taking the derivative until you get to whatever derivative they want you to find. So in this case, they ask us to find the second derivative, f double prime. In order to get there, you need the first derivative. So if I find the first derivative, I have 8x cubed. 3 times 3 would be 9x squared minus 4. And then second derivative, let's just take the derivative again, 24x squared and 18x. Now, if they ask for the third derivative, fourth derivative, third derivative, and they didn't ask for this problem, but third derivative, they'll use 3 primes. So it'll be 48x plus 18. Fourth derivative, at this point and beyond, they'll just use a little numerical value there. They'll just write it. It looks like an exponent. It's not an exponent there. So that would be 48. Fifth derivative is going to be 0, and every derivative after that would also be 0. Sometimes the polynomial functions will do that. Eventually the derivative will be 0, but some of them they could just keep going on forever, like sines and cosines, the trig functions. You can keep taking the derivatives. So higher order derivatives, you have a few towards the end that they ask you to do that. And then if you go back, this we skipped over this page. You had these 2 graphs here, and they ask you to find h prime of 3 and p prime of 3. They want you to use the graph to come up with that. So the first one here, they said h of x, so that's equal to f of x times g of x. So if I want the derivative of h, I need to do product rule. So it's going to be the first function of x times the derivative of the second, which is g prime, plus the second function, which is g of x, times the derivative of the first function, which is f prime of x. So that's my formula, and they said, let's figure this out when x is equal to 3. So I want f of 3 times g prime of 3 plus g of 3 times f prime of 3. So you're going to use the graphs then to come up with these values. So f of 3, you know how to do that. That was back from algebra. So here's 3. F of 3, f is the pink function. If I come up here, the height for that is 8. I'm going to do this next term in a second. G of 3, I know how to do that as well. G of 3, that's this value right here. Looks like a half. We're going to say it's a half. All right, so G of 3 and F of 3 we're able to figure out. G prime of 3, F prime of 3, that's the derivative. So if you're looking at this graph at 3, when they say G prime of 3 in this term, they want the slope for this line at 3, and that's my graph of G. So the slope for that graph, let's see, it went down 1 and to the right 2. So its slope is negative 1/2. So G prime or F prime, they're talking about the slope. If it's F or G, they're talking about the height. And then F prime of 3, that's up here, this slope is equal to 0. So what do I have? Negative 4, it looks like, then, for H prime of 3, because this is going to be 0. So that's the idea. You can do the same thing for P of X. We need our quotient rule to start. So P prime of X would be the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom function squared. And if we plug in that value of 6, I would need G of 6 times F prime of 6, which is the slope at 6. Oops, minus F of 6, G prime of 6, all over G of 6 squared. Right, so G of 6, that's the height for the G function, which is green at 6. So here's 6. That height looks like it's at 3. F prime of 6, that's the other function, F prime of 6. So the slope for this segment right here looks like it's 1, 2, 3, 4, 5 over 2. Rise over run. Looks like 5 halves. And then F of 6, so that's the pink function. The height at 6 was equal to 9. G prime of 6, so at 6, here's the slope for the green line there, which is 0. Over G of 6 squared, and G of 6, we said that height was 3. So that's equal to 0. I have 15 halves divided by 9. If I multiply top and bottom by 2, that'll get rid of the complex fraction. So I have 15 over 18, which we reduce to what, 5 over 6. 3 will go into each of those. Great, you have a few problems at the end that look like that.